In this lesson, we're going to talk about centripetal force and elevators. Centripetal force is essential to understanding how objects can move in circular motion, while elevators are all about linear motion, up or down. We're starting with centripetal force. The main idea is that centripetal force is inertial force that acts in the direction of the object's motion. If an object is moving in a circle, there is some force acting upon it to cause it to deviate from its straight line path, accelerate inwards, and move along a circular path. Object that moves in a circle has acceleration even if the speed is constant, because it is always changing directions. The object is always turning since it's not going in a straight line. According to Newton's second law of motion, that net force equals mass times acceleration, an object that has mass and acceleration has net force. In circular motion, this force is directed inwards, or towards the center of the circle as the Y diagram shows. This force is called centripetal force. It's also important to know that tangential speed occurs when velocity is tangent to force or acceleration. To make it more obvious, speed as vector is perpendicular to circle's radius.
Circular motion has two different important calculations: velocity and acceleration. In terms of velocity, it is calculated perpendicular to the acceleration and can be thought of as circumference over the time it takes to complete a revolution. Acceleration, however, is pointed at the center. Same with centripetal force, which can be calculated with velocity squared over radius.
In real life, centripetal force occurs plenty of time during any instances of turning or rotation. In this space example, Moon revolves around Earth in a near-circular orbit due to centripetal force. As the Moon orbits the Earth, the force of gravity acting upon the Moon provides the centripetal force necessary for circular motion. Let's solve the first question. A stone on the end of a string is whirled clockwise at constant speed in a horizontal circle as shown in the diagram below. Which pair of airs best represents the directions of the stone's velocity, v, and acceleration, a, at the position shown?
For the first region's question, once again velocity is tangent to the circle and acceleration points inward.
Now let's move on to the second question. A baby and stroller have a total mass of 20 kilograms. A force of 36 newtons keeps the stroller moving in a circular path with a radius of 5 meters. Calculate the speed at which the stroller moves around the curve.
For the second region's question, one can use the given force to calculate the acceleration using centripetal force is equal to mass times centripetal acceleration. Then from there, one can use the equation velocity squared over radius to find the velocity, which is 3 meters per second.
Now the third question. A 28-gram rubber stopper is attached to a string and whirled clockwise in a horizontal circle with a radius of 0.8 meter. The diagram below represents the motion of the rubber stopper. The stopper maintains a constant speed of 2.5 meters per second. Calculate the magnitude of the centripetal acceleration of the stopper in the diagram below.
For the third, you have to use given velocity, plug it into the equation, and find the acceleration. An elevator accelerating up or down affects the force and apparent weight over the objects inside. At constant speed, or when not moving, an object's weight remains unchanged. When accelerating upwards, force and weight increases on an object, as force is now being added to normal force, which is the force of the ground pushing up. The same is true for downward acceleration, which causes a decrease in normal force.
This slide is all about equilibrium versus non-equilibrium real-life situations. People skating at constant speed in a straight-line path is an example of equilibrium. Once something is in motion, when there is no net force to change the state of motion, it is in equilibrium. Now let's focus to the right. Person accelerating upwards or downwards in an elevator signifies that the forces are unbalanced due to acceleration, meaning that this is an example of non-equilibrium. This question reads, a person is standing on a bathroom scale in an elevator car. If the scale reads a value greater than the weight of the person at rest, the elevator could be moving.
For the fourth, because the weight is greater, you know the normal force has increased, which means that the object is accelerating upwards.
Let's move on to this question. A man is standing on a scale in an elevator and notices that the scale reads 30 newtons greater than his normal weight. Which type of movement of the elevator could cause this greater than normal reading?
For the fifth question, once again, a 30 Newton increase indicates accelerating upwards as normal force depicts upwards force. For the sixth and final question, the term constant speed is an indicator of no acceleration, which means that the car is at equilibrium.